Did you know the next limit for artificial intelligence is not just compute, it is memory? Hello, explorers. Today we step inside the layer of the AI stack that decides whether models fly or stall, the place that sets the price of training, the cost of inference, and the size of the power bill. This is the hidden bottleneck reshaping AI. Start with bandwidth. Modern accelerators push tensors at breathtaking speed. High bandwidth memory sits right beside the compute die, so data arrives on time. Demand for these stacks grew faster than factories could expand. Packaging lines that bond compute and memory on complex substrates became the new gating factor. When packaging is tight, delivery dates slip, server prices climb, and projects miss windows. Follow the costs. Memory now drives total system price more than many expect. Adding stacks raises bill of materials and can reduce yield. Skimp on memory and you pay elsewhere. Models must shard across more devices. Traffic spills onto the network, and every extra hop burns time and power. Hidden costs accumulate in longer schedules, bigger clusters, and higher cooling needs. Look at power. Moving data is expensive in watts. Larger models with longer context windows move more bytes per token. That pushes racks toward liquid cooling and pushes facilities toward higher density power delivery. Memory temperature moves on to the critical path for uptime. The result is that a choice about memory becomes a choice about energy and real estate. Now the fixes. One path is more and faster memory near the die. HBM generations keep improving bandwidth per stack and capacity per package. Another path is to stop treating memory as one box per server. New interconnect standards allow memory pooling across nodes over coherent links. Pooling does not replace near memory, but it reduces stranded capacity and raises utilization across a fleet. Storage class memory and fast flash help with checkpoints and retrieval, but they do not replace the near instant access that HBM provides. There is also the software path. Smaller expert models route tokens only where needed, cutting memory traffic and compute at the same time. Quantization reduces precision where safe, shrinking tensors, and increasing effective bandwidth. Efficient attention and windowed context keep sequence length under control without capping capability. Retrieval augmented generation adds facts without exploding memory footprints. None of these steps is free, but together they bring memory demand back within reach. Hiring tells the same story. The most valuable engineers now speak both model math and memory math. They understand kernel fusion, graph compilation, cache behavior, and the difference between local bandwidth and fabric bandwidth. Facilities teams hire for liquid cooling design, power planning, and high-speed interconnects. Supply leaders cultivate second sources for memory and packaging, so a single hiccup does not stall a roadmap. The best teams connect a token-level decision in a transformer to a thermal change on a memory stack. Leaders need a practical playbook. First, model true memory cost. Count module price, packaging yield, power, and cooling as one figure. Second, profile workloads. Measure bytes moved per token and the fraction of time lost to communication. Third, diversify supply. A qualified alternative for memory or packaging can be the difference between shipping and waiting. Fourth, plan power early with your utility. Interconnect queues and substation timelines now decide launch dates as surely as code freezes. What is next? Expect capacity expansions from memory makers and packaging partners, plus new form factors that place more stacks nearer to compute. Expect memory pooling fabrics to move from pilots to production for retrieval-heavy and memory-hungry services. Expect customers and regulators to ask for energy per query, not just speed. Expect model design to care less about parameter count and more about how efficiently you feed those parameters. The bottleneck is not a dead end. It is a forcing function. It pushes us to design models that are smarter about bandwidth, facilities that are smarter about power, and teams that are smarter about trade-offs. If we meet it with clear design and honest math, AI becomes more capable and more sustainable. If we ignore it, the bill arrives in delays, overruns, and black boxes that run hot and slow. So here's the takeaway. Memory is not an afterthought. It is the engine room. Treat it that way, and you will build systems that are faster, cheaper, and greener. Comment your thoughts. Like this video if it clarified where the real bottleneck lives. Subscribe for more clear-eyed looks at the machinery behind intelligent systems, only here on Next Gen Science. Let us keep exploring together.